All right, we have talked about free fall some. Section 4.3 deals with projectile motion. And this is a free fall problem. But with a non-trivial initial velocity. What I mean by that is the initial velocity is not in the same direction as the acceleration. So that forces us into two dimensions, right? So what happens in the free fall problems that we've done already, either something is thrown straight up or straight down. We know that acceleration is always down in a free fall problem. So the acceleration doesn't change the direction of our velocity, so you get 1d. So that means in order to get a 2D situation, we need, well, acceleration's down, that's not going to change. So we need a velocity that has a non-zero x component, right? All right, what about if the y component is 0, as in my example here? Is that a problem? What's going to happen? Well, our acceleration in the y direction is non-zero, so it's not going to stay 0. We're going to get a y component at some point in any one of these. So that's just kind of a special case that gives you a little more knowledge about how to break down the problem. But there's nothing special with it. So what I'd like to look at first is just an XY plot, right? Rather than a time plot here, we've done a lot of X versus T with an X on the dependent axis and a T on the independent axis. Here I'd like to just plot X and Y versus each other. And if we were to consider a time here, it would be as we move along the graph. So let's imagine that we have a projectile that follows this path and consider what the velocity looks like at each point along the curve. We said that instantaneous velocity is a tangent, right? So there, 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 there. And this one didn't really line up right. There, that looks a little better. And I'm drawing this one, trying to get it as correct as possible to make my point. All right, keying in again, our accelerations in the y direction. What does that mean about AY? Well, AY is just that value, and AX is 0. So AX is 0. This implies that VX is constant. If you ever see me use this notation, it means constant. A double-sided arrow over a value means that value is constant. All right. So if Vx is constant, then all these blue arrows I'm drawing are the same length. Right? Vx doesn't change. what happens to Vy? Right? It starts out upward with a large magnitude and it's slowing down. Here it's 0. And then it's accelerating downward. All right, so if we consider just Vy, what does that graph look like? So let's graph Vy versus t. If we were to graph Vy versus t, it starts out with a large positive value, and I didn't draw my graph where you can access everything. It starts out with a large positive value, goes to 0, and then has a large negative value. And Vx is constant, so I won't bother graphing it. But I think it's important to realize this part, because remember when we were doing one-dimensional free fall problems, at the top, V was 0. But you'll note here that V is not 0 at the top. V in the y direction is 0. So it's an important distinction to make when you're doing a projectile motion problem, that while you don't know the velocity, you do know the y component of the velocity at the top. All right, that point where you're passing through the axis here. All right, what more do I want to say? All of our kinematics equations hold. But we have to apply what we talked about in the video for 4.2, that it's a vector equation. So if I have my position equation, which I'm now going to write explicitly as a vector equation, then I can break that into components. So I can say, left my initial value off there. Now I can say this equation is true in X and it's true in Y. And if we consider this from the point of view of our XY plot, this is the parametric representation. Right, we have an additional parameter, time, that shows the relationship between the X and Y values. All right, and if we're in free fall, we can restrict these even more, right? Because we know that AX is 0. And we know that AY is G in the downward direction. So we end up with this. And this is why we reviewed using the quadratic formula in our algebra review. You're going to run into using the quadratic formula here to find time. All right, this is the basic information. I do want to talk about problem solving a little bit though, although we will in class as well. Because of this separation of X and Y variables with the parameter t, t is shared. X and Y variables don't interact directly. What that means is I should never have a kinemax equation where I put not even like that. How about this? I should never have a kinemax equation that looks like this. I haven't set up enough of the information. It's very hard to do it without going into a specific example. If you're doing something in the x direction, an x equation should not have g in it. Right? Because g is your y acceleration. And likewise, any x or y component should not appear in a y or x equation. And I'm talking about your initial equations here. Once you start relating things and substituting, some of that stuff may mix together if you're eliminating variables, right? But in your initial physical setup, they should never interact. Also, the total vector should not be used. The components are. So the only way that you would use a total vector is if it is vertical or horizontal, meaning that the other component is 0. So in this case, A is equal to AY, and B is equal to BY, because they're only in a vertical or horizontal direction. For any vector that's at some angle relative to your coordinate axes, you'll have some non-zero values, right? So you'll have a cx times, I put a y here, this should be an x, sorry. You'll have a cx in the x direction and a cy in the y direction, right? Important things to remember, just kind of catch-alls. C is always greater than or equal to one of its components, right? Because it's the hypotenuse. So the only case they're equal is where the other one is 0. And the two components will always add up to at least as much as the entire vector. So this is the, man, I can't remember what the theorem is called at the moment. But there's a theorem in algebra that says if you add two vectors, it's a triangle postulate or something. If we say A, B, add to C, then C is less than or equal to the length of A plus B. Right? And the only way that it could be equal is if they were all in the same direction. And I've already said up here also that it is at least as big That's not true, because they could be opposing each other. Yeah, this is not true. What I was trying to get at is this triangle relationship. this is true for components. It's not true for generic vectors. This is true all the time. Sorry for the confusion on that. This is true for components. It's not true in general, but it is true for components. This one's true in general. And I'm getting off track. We'll just stop there because I've already finished talking about projectile motion and I'm really off track.